Dear students, today our topic is electrostatics. This is a very important topic for all the students of class 12. Now, at the beginning, we discussed about the concept of electrostatic force and electrostatic field. For these students, we all know that the important characteristics of any matter is its mass. Because mass measures the inertial property of any material or any body. Like this, mass carries an important role in mechanics. Similar way, charge, it is denoted by Q, has an important property for the study of electricity. There is a relationship between mass and charge. For mass, if we find any elementary particle in nature, if it is massless, then it is also chargeless. For example, we can consider photon or neutrino also. They are well-known massless, chargeless particle. So, charge cannot exist in nature without any mass. But the reverse is not true. If any particle is there of mass m, it can be without any charge. That is, it can be chargeless. If we consider any bulk matter consists of many atoms. And if we consider one of the atoms, there is electron and proton, two charged particles. But the number of protons and electrons are equal. So the atom is basically chargeless. As a whole, total bulk matter is also chargeless. But if we can destroy the balance of the number of proton and electron, then the atom becomes charged particle, and hence the total bulk matter will also be charged. If there is excess number of electron, then the material becomes negatively charged, and if there lack of electron, then the material becomes positively charged. So in nature there exist two types of charge. One is positive and the second is negative. Now we consider two bodies of charge Q1 and Q2. We can write the amount of charge Q1 is equal to N1E and Q2 is equal to N2E, where N is basic unit is called electronic charge. E is equal to 1.6 into 10 to the power minus 19 coulomb. So any charge in nature can be expressed in terms of a basic unit, and the basic unit is nothing but the electronic charge. This principle is called quantization of charge. Here N1 and N2 are integers, that is 1, 2, 3, etc. If we want to understand the term quantization, then we have to consider a ladder. If we want to climb a ladder, then we can put our leg on first rung or second rung or third rung or fourth rung, but we cannot put our foot in between any space in between first rung and second rung, or in between second rung and third rung. So we can say the system of this ladder is a discrete system. If I say that you can put your leg only on the even number of rung, that is second rung, fourth rung, sixth rung, eighth rung, etc., then you cannot put your leg on the odd number of rung, that is 1, 5, 3, 5, etc. So I impose external condition on the discreteness of this system, then the system is called quantized. Here, for the case of charge, the condition is n1 and n2 should be integers. So the fractional value 130 or 230, etc., or this amount of charge are not possible. So this principle is called quantization of charge. Like this, second principle is also there, and we call the principle as conservation of charge. According to this principle, if we consider isolated system, the total charge of the isolated system remain constant for all times. That is, there is a boundary, and this boundary is electrical insulator. That is, the boundary cannot allow to enter or to escape the charge from this system. Hence, total charge of this system remains constant for all the time, and this principle is called conservation of charge. We have to notice that here the number of positive charge and number of negative charge should not be conserved individually, but the total number remains constant. For example, we can take a reaction that gamma photon can produce electron as well as a positron, and this type of reaction is called pair production. If this type of reaction is held in this system, then total number will be unchanged, but the number of electrons and number of positrons individually can change. So this type of reaction or pair production does not violate the principle of conservation of charge. Next, we discuss about the electrostatic force, and this force can be calculated from Coulomb's law. For this, we consider two different charge body, Q1 and Q2, and we can write Q1 is equal to N1E and Q2 is equal to N2E. N1 N2 are integers, and E is the basic unit we called this electronic charge. Now here in 1 or in 2, the integers number are very small with respect to the spatial dimension of the charge body. Then we can consider the charge distribution as discrete charge distribution, as well as when N1 and N2 are very small with respect to the spatial dimension of the charged body. But if N1 and N2 are not very small but large quantity, then we call the system have continuous charge distribution. For these two type of charge distribution, we have to calculate the force as well as field into different way. So now, first we consider the discrete system. Two charge particles are there, and we attach a coordinate system with it. Let three axes are there, x, y, and z, with origin O, and we consider two charge particles q1 and q2 with position vectors r1 and R2. Then the separation between the two charge, we can write it R21 vector. According to the law of addition of vector, we can write R21 vector is equal to R2 vector minus R1 vector. Now, if we calculate the force in between the two charges Q1 and Q2, we have to apply Coulomb's law. Coulomb's law is strictly applicable for point charges. That is, the spatial dimension of the two charged body is very small with respect to their separation or intermediate distance between the two charges. And another condition for the application of Coulomb's law is the two charge particles Q1 and Q2 always at rest, that is their velocities are 0. If velocity exists, then magnetic force also arises, and we want to calculate the electrostatic force. Hence, we consider the velocities of both the charge Q1 and Q2 is equal to 0. Now, the force between Q1 and Q2, we can write it that force is equal to F21, and it indicates the force on charge Q2 due to Q1. So this is a convention to write the force as F21, which expresses the force on charge Q2 due to Q1. Coulomb force, we all know that this is a inverse square law force. Hence, the force proportional to 1 by distance square, so R21 square. And also, if the magnitude of charge increases, the force increases. Hence, the force proportional to Q1 as well as proportional to Q2. Hence, we can write the force F21 directly proportional to the product of the two charges Q1 and Q2. If we combine these two equations, then we can write F21 directly proportional to Q1 Q2 divided by R21 square. And we can write this as the equation by using a proportionality constant, which is denoted by K. K is nothing but a proportionality constant, K Q1 Q2 by R21 square. Here K is a proportionality constant and its value depends on the intermediate medium in between the two charges Q1 and Q2 and the unit system which we use for this calculation. We discuss for SI system, and we can write these equations with the constant F21 is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R21 square. As force is a vector quantity, so we can use vector sign with a unit vector R21 cap. R21 cap is a unit vector in the direction of the R21 vector. And here we use the constant 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught. Epsilon naught is called electrical permittivity of free space or vacuum. The value of epsilon naught is equal to 8.854 into 10 to the power minus 12, and its unit will be, we can calculate from here, unit of SI unit of charge will be Coulomb, distance meter, and force Newton. Hence the unit Coulomb square per Newton meter square. when we calculate the value of 1 by 4 pi epsilon naught, its value will be almost 9 into 10 to the power 9, and its unit will be Newton meter square per coulomb square. If the medium or the intermediate space between the two charges is filled up with another medium, any other medium, then we can write the constant as epsilon, and epsilon is called the electrical permittivity of that particular medium, where the relation between epsilon and epsilon naught is epsilon is equal to k times epsilon naught, and k is called dielectric constant of that medium. This is a very important constant. If any medium has a higher value of dielectric constant, it can reduces the force more, electrostatic force more. Now we can write the value of force F21 is equal to 1 by 4 pi epsilon naught Q1 Q2 by R 21 square R21 cap. Similar, this force represents the force on the charge Q2 due to Q1. Similarly, we can represent the opposite force, that is the force on the charge Q1 due to charge Q2, and this notation will be F12 vector is equal to 1 by 4 pi epsilon naught Q1 Q2 R12 square R12 cap. The basic relation between the unit vectors R21 and R12, we know R21 is equal to minus of R12. Hence, we can write the two forces F21 vector will be in the opposite direction of F12 vector. So the magnitude of two forces are equal, but they are in opposite direction. This is the mathematical expression of Coulomb's law, from where we can calculate the electrostatic force in between any two charges, and the two charges are at rest, that is their velocities are 0. Now we can see, as this force is proportional to 1 by r square, so if we put r tends to infinity, then the force becomes 0. That is, this force is a long range force. If the distance tends to infinite, then the force becomes 0. But there is experimental evidence to believe that for short range, this force vanishes over a region of dimension 10 to the power minus 15 meter, that is nuclear diameter. We now calculate the field, electrostatic field for any charged particle. For this, the first question that will arise, what is field? For this, we can say for gravitational field, if we consider any mass m near the Earth's surface, then due to gravitational attraction, the mass will attracted by Earth. That is, we can say Earth spreads out its field of influence in the space surrounding it. How can we quantify this? To quantify this property, we can divide this gravitational force by the mass of that particle, and we get g, which is called gravitational acceleration. Its value is independent of the mass of the particle, and its constant. It is same for all the objects. In a similar way, we calculate the electrostatic force from Coulomb's law, but if we divide the force with charge, that is the dimension of or unit of Newton per Coulomb, this quantity is called electrostatic field. To understand properly this fact, we consider a charge capital Q and consider another charge small q. Position vector of capital Q and small q r dash and r vector from origin O, and the separation between the two charges capital R. From the relation of vector addition, here we can write capital R vector is equal to R vector minus R prime vector. The force will be F is equal to 1 by 4 pi epsilon naught Q divided by R square. Now, if we divide the force with the value of charge small q, then we get F by Q is equal to 1 by 4 pi epsilon naught Q by R square. This value we can say as electrostatic field of the charge capital Q. But here the reverse force also exists, and we can write from this equation, if we say the field is E, then here we can say the field E dash is equal to F by capital Q, and its value will be 1 by 4 pi epsilon naught Q by R square. Both the fields are present. This is the field of capital Q charge and this is the field of small q. So there is interaction in between the two fields. If we measure this field, we should try to minimize this field E dash, and for this we have to take the value of small q very small with respect to capital Q. If we take very small amount or small value of q, then this value will be greater and this value decreases. Hence, we can neglect this field E dash with respect to E. Hence, there is a conception to take the limit of small q as small as possible, and we can express this as limit q tends to 0 F by Q. This is the definition of electrostatic field. The field has a unit, SI unit, Newton per Coulomb or Newton Coulomb to the power -1. Now, this electric field, if we interpret the electric field geometrically, the process was first introduced by Faraday and it is called electric field lines. Electric field lines are curved line drawn in such a way that its tangent drawn at any point gives the direction of electric field at that particular point. And also the intensity of the electric field can be represented by the density of field line, that is the lines crossing per unit area normally or in a perpendicular direction. Here, if we consider a charge Q, according to Maxwell, number of field lines coming out from this charge Q will be Q by epsilon naught. Now we consider an imaginary sphere with the charge small q at its center. Then the number of field lines is q by epsilon naught, and if the radius of this sphere is r, then the surface area of this sphere we know 4 pi r square. Hence, number of field lines per unit area 4 pi r square. So this value will be 1 by 4 pi epsilon naught q by r square, which is the intensity of electric field. So it is proved that the intensity of the electric field is represented by the density of field lines, that is the number of field lines passing through unit area normally or in a perpendicular direction. For a point charge plus q, we can draw the field lines. If we want to find the mathematical equations of the field lines, we can write r vector. R is a function of s, is a general equation of curve, and dr ds, it will be a tangent vector of this curve. Now we can write the component of this tangent vector as dx ds, dy ds, and dz ds. If we draw the curve, then electric field is also tangent in a tangential direction of this curve, and this represents also the tangent. So electric field E vector and this tangent vector are parallel basically. So we can write dr ds is equal to some constant alpha times E, and we can write with the components value. E has three components, Ex, Ey, and Ez. So we can write dx ds is equal to alpha Ex, dy ds is equal to alpha Ey, and dz ds is equal to alpha Ez. For simplification or very easy calculation, we can consider for 2D or two-dimensional geometry, we can neglect the z component and we can consider these two components. So we can write from this dx by ex is equal to alpha ds and dy by ey alpha ds. Hence basically we get dx by ex is equal to dy by ey. Now, if we represent the electric field vector E is equal to 1 by 4 pi epsilon naught q r cube, r vector is equal to 1 by 4 pi epsilon naught q by r cube x I cap and y j cap. We can calculate Ex by Ey is equal to, from here, Ex by Ey is equal to dx by dy, and here Ex by Ey is equal to x by y. Hence we can write dx by dy is equal to x by y, or dx by x is equal to dy by y. Integrating, we get ln x is equal to ln y plus ln c. Or in a reverse manner, we can write ln y is equal to ln x plus ln c, or y is equal to cx. This is the equation of straight line. Hence, we can represent the field line of a charged particle as straight line passing through origin. And as we take the test charge as plus 1 coulomb charge, so direction of the field line we take outward. This will be the representation straight line passing through origin. Thank you, students.